I'm waiting my iPad, let my pencil turn. We're looking at test 6 here. You have section 7.1, 2, 3, and 4. 7.1 and 2 was about momentum and impulse. 7.3 was conservation of momentum. And 7.4 was inelastic versus elastic collisions. So those are the main topics that we studied. But what we really want to focus on here, and we see this a lot, are the formulas involved. And those formulas tell us a lot about what's going on. So in 7.1, we had momentum impulse theory and momentum. We started with the basic formula that momentum is a function of two things, mass and velocity. I'm going to give like a 20-minute spiel, and then I'll give you time for questions. Give you a little time for questions. So momentum and velocity. If momentum goes up, if mass goes up, momentum goes up. If velocity goes up, momentum goes up. But the idea is that both parameters are directly related to the momentum. We've also asked questions, and I've asked you guys these questions like, what if the momentum doubles and the velocity triples? Then what is the, I keep saying momentum. What if the mass doubles and the velocity triples? What happens to the overall momentum of the system? So how would I approach a problem like that? If the mass doubles and the velocity triples. We did this with kinetic energy in the last test. Chris, what do you think?
I think like you would create an equation equals 2m 3v.
Yeah. Create an equation with P equals 2m times 3v. If you're told the mass doubles, just literally write 2m. If you're told the velocity triples, write 3m. What if the mass were cut in half? What if I say the mass is cut in half? M over 2. What if it says the velocity is quartered? If the velocity is quartered, how do I write that? V over 4. Now, what I do next is the same for all of these problems. No matter what I tell you the numbers are, the next step is the same. We then look at this and say, let's put MV together, and then let's put our numbers in front. And these numbers, 3 times 2, give us just 6. So if I want to compare what happens from the old momentum to the new momentum, just look at the coefficient. Clearly the momentum goes up by a factor of 6. By a factor of 6. If the momentum were a decimal, and then MV, what could you tell the M? At the other hand. If the momentum were a decimal value and then MV, instead of the number 6, a decimal and then MV. By decimal, I mean a decimal between 0 and 1. Maria? We'll go down. If your overall answer says 0.9 MV, what's 0.9 as a fraction? What's 0.9 as a fraction?
9 over 10.
Yeah, 9/10. And what that would say is really, it's 9/10 of what it was. This is saying it's 6 times as big as what it was. This was the original momentum. This is the new momentum based on the changing parameters. If the parameters change, the momentum will most likely change. Unless it says something like the mass is tripled and the velocity is cut in 3. Then what's the answer? If the mass is tripled and the velocity is cut in 3, how would you respond to that? What's the overall? I'm trying to lock the screen, guys, sorry. And I cut the velocity in 3, what's going to happen? Those cancel, you get back to MV. So there'd be no effect on the answer from here to here. That's a different scenario. So depending on what that is. So we understand that these two things are directly related to the momentum itself. How about to each other? How are mass and velocity related? If an object can only have a certain amount of momentum, right? But it gains mass. We did this example in class a couple times with the carts. The cart is moving, and then suddenly it combines with another cart, and now they're more heavy, or they're more massive. And what happens to the cart as a result? Slows down. So if I gain mass, and my momentum is constant, I must be losing velocity, and vice versa. Okay? All right. If you gain mass while your momentum is constant, you must be losing velocity. So it's like, imagine you're running. If you're running as hard as you can, right? You're running as fast as you can't have any more momentum than what you currently have. If suddenly you have weights on your shoulder, what's going to happen to your body naturally? If you add weight and you're running, you'll slow down naturally. Because you can't run as fast carrying that weight. Because you have a limit to the amount of momentum you can actually exert. It's like power in a sense, okay? It's not the same with the concept of running at a certain rate. Yeah? No? All right, 7.2, we did these together. 7.2 went into momentum impulse theory. Let's jot that down on the next slide. Momentum impulse theory told me the change in momentum is equal to the impulse. So Ft is impulse, for those that keep forgetting this. This is impulse, the product of F and T. And F is the force that's causing the object to change momentum. F is the force. It could be friction, it could be a push, a pull, it could be a magnetic force, it could be an electric force, it could be any force. The force that's causing a momentum change. That's what F is. And what's T? What's T? I mean, I know what the T stands for, but in these kinds of problems, T is what specifically?
Second.
Okay. In this problem specifically. Specifically, good. Come on, man. Specifically for these problems. The time that. Very good. There it is. T is not just time. Time is whatever it is. T is the time that the force acts on the body. So a force acting on an object causes a change in momentum because that force acts on the object for a given time period. So the product of these two will represent how much momentum you change by. So if I know how much momentum you change by, and you know the force, you could solve for time right away. If you know the delta P, momentum change, and you know the force, you can find time. If you know force and time, you can find the momentum change. But what if you're not given the actual momentum change? What if you're given velocities and masses, right? We have to break up what does delta P actually mean. And delta means change, and change means what minus what? Yeah, good. Final minus initial. So I can use this formula now. If I'm given the final momentum and I'm given the initial momentum, I can plug them in directly here and here. And maybe I'm given the time, then I find the force. But let's go one step further. If I'm given masses and velocities, I need to write down the definition of momentum. So I've got two momentums here. This is the first one, and this is the second one. So any of these three formulas any of these three can be used on the test tomorrow, depending upon what you're given. If you're given mass and VI and VF and T, then find F. If you're given F and T and VI and VF, find the mass. Depends on what you're given. But you could use any of these three formulas. Which of them is given on your formula sheet? Which of these formulas is on the formula sheet? The first one. So get familiar with changing this, please. This is on the formula sheet right here, what's circled. The other two come from that other formula. What kind of a force do you get as an answer if you're causing something to lose momentum? If I'm causing you to lose momentum, what kind of a force must that be? Friction is an example, very good. But generally, you gave me a specific force, generally. Opposing, good. One more step. Mathematically, what do I call that? A negative force, opposing. Any opposing force, it opposes motion, opposing, causes the motion to decrease or the momentum to decrease. What if your momentum increases? What can you say about the force? It's a positive force. Okay? It's a positive force. Want an example of that? When you learned to ride a bike as a kid, you had training wheels in the back, right? Maybe mom or dad tried to help you. What would they do? They'd stand behind you and they'd push you along the whole way, right? Because your legs weren't so strong as a little kid, you couldn't really push to a certain speed. If you wanted to actually get to learn how to balance on a bike, you have to go fast enough to balance. So they would start with their hand on your back and they'd be pushing you along. What are they doing? They're giving you momentum. They're increasing your velocity by pushing you, by applying a force for a given time period in the positive direction. That's a great example, okay? Any example where a force is applied, okay, will cause a change in momentum, provided the object does indeed move. Okay, it does indeed move. We talked about force and time and how they are related. The force felt on an object and the time of contact. What did we discuss at length in this section? We talked about it for a little while in class. It was very conceptual, the idea. Yeah, the airbags we used as an example. What else? In class with notes, I talked about something. Airbags was one thing we did mention. I think that was in both classes, actually, airbags came up. What else? There's one more. Remember I did the egg toss or the water balloon toss? What did we conclude with that process when we went through that idea?
You catch like momentum, then it will impact less.
Okay, I like the way you're saying it. Let's change a little bit of it up. But the impact is less for sure. So Peter said when I do this, right? When I do this, the force or the impact is less. Why is that? Very good. The more contact time you make, I'm contacting the egg for like a full second when I'm decelerating it. I'm increasing T, aren't I? And if I'm increasing T, and this is not going to change, this is a constant, to increase this, this has to go down. Again, pick a number. Make this entire left-hand side 10. If this is 10, this is 1. If I increase it to 20, this becomes a half. So those are indirectly related. The more time you have to slow down, the less force you need to apply. You need to apply in that case. The same thing with a car. How many of you have been in the car with mom and dad, and you're on like the turnpike, or you're somewhere where you're traveling at like 70 miles an hour, and then they realize that there's a lot of traffic up ahead, and sometimes they have to hit the brakes a little hard, right? You feel that forward motion because of inertia, we know, right? But the idea is that the force that the seatbelt pushes against you has to be a really high force, because your parents are lowering your momentum real quick by slamming the brakes. If you hit the brakes lightly, don't you slow down slowly? And it takes a lot of time to slow down. That's an increase in time, and you don't feel it on your body as much. You don't feel the G-forces as much on your body. So the concept here is that more time is less force. Less force. In the other class, is it Shannon that rides horses, right? Does Shannon ride horses, is this correct? Because we brought it up and they all started staring at her, so I kind of picked up on what they were doing. We were talking about horse riders and impact. When a horse is galloping, horse riders, if the horse is walking and you're on a horse like back in the day, not anymore, but if you took a horse to travel long distances, you wouldn't run the horse to the ground or else it would die. So the horse would normally walk, and it's a trot. And you could sit on the horse back and just trot. But if a horse is actually galloping and running, are the horseback riders actually sitting? What are they doing? How do they support themselves usually? What's the whole concept there? Yeah.
When they like squatting up.
Yeah, exactly. Very good. I like it. They're doing this. And squatting. That's a weird thing to do, right? But imagine you're sitting on something. So they're literally squatting. So whenever the horse gallops, that impact takes time. Their legs do this every time. Their legs are absorbing the shock every time the horse hits the ground. So their legs are increasing the time that they are kind of slowing their body down from hitting down. Versus every time you gallop, imagine your butt just going, like literally, like your butt bone hitting the back of the horse. That would probably hurt a lot. And it would be like, it'd be a short time period, right? I think I gave the example of jumping off a chair with your knees locked. Imagine jumping off a chair. And go try this, please. Try it from a lower height. Something like maybe a half a foot off the ground. Lock your knees and then jump off. It's going to hurt. So don't do it from a high height. It will definitely hurt. You'll feel it vibrate through your jaw and your body.
My dad last year broke his pelvis because he was running, and it was like a speed bump, and he hit it with like his leg like still like this, not like that. And it shattered his pelvis.
It shattered his pelvis back here from his foot impact.
Yeah.
That's crazy. Yeah, that's the force being propagated through the rest of your body to like a weaker point. That must have been the weakest point that broke. Ooh, that's terrible. But the concept, right? More force comes from less time. More time yields less force. Peter, focus. Come on. The section 7.3 and 7.4 stuff are very similar to one another. We talked about collisions or explosions. That's really what we have going on here. We have many possibilities with one governing equation. And there it is. That's the one governing equation that you use to derive all others. And if you recall, the other two equations are also given on your formula sheet. Okay, one of them looks like this. And this is the equation for elastic collisions. And I know it's elastic collisions because elastic collisions have separation afterward. They don't stick together. So this is the elastic equation we'd always use. When they stick together, we have inelastic. Okay, with inelastic, we just lump those masses together. So they start separately, and they might not both be moving. So some of these might go to zero. But the key here is that they end together. Okay, they end together. What else do we know about elastic versus inelastic? So this is one, right, significant difference. Inelastic, they stick together. Elastic, they separate afterward. What else do we know about these types of collisions? With elastic and inelastic, think about your most recent lab that you've been working on. Or tell me something. Go ahead, Alex.
Isn't that momentum remains the same in elastic, while in inelastic, kinetic energy doesn't remain the same.
Correct. So it's the energy we want to really focus on. Momentum is always conserved, right? Always. Whether it's elastic or inelastic, both of these equations are true, and these equations are giving us conservation of momentum. But the kinetic energy, whoops. Come on. Kinetic energy change occurs sometimes. Here, there's no kinetic energy loss at all. So that's true for elastic. The initial kinetic energy will always equal the final for elastic. For inelastic, it's not true. You'll have a delta energy. And that's final minus initial. It's not going to be zero. Okay, so in the first case, you could have said the change in energy equals zero, which leads us to say that KE initial must equal KE final. There's no change in energy or no energy loss. Whereas here there is energy loss, and this is how we're going to calculate it. Now, let's point some stuff out, because I feel like people are getting confused a little bit in the lab, so I want to make sure we're all clear on stuff. So here, when I calculate the final kinetic energy, how many objects physically are moving at the end of this problem? How many kinetic energy calculations do I have to do at the end of the problem? Catherine?
One.
Simply one. At the end of the problem, they fuse together. So you use 1/2 mv squared, but m is the sum of these two, and this is the v you're going to square. In the beginning of the problem, though, KE initial, there are two objects moving, possibly, maybe only one, but hypothetically right now, both are moving. So we'd have kinetic energy from the first object, and then another formula to get kinetic energy from the second object. We'd add those kinetic energies together, and that goes in for KEI. So if two are moving, you have two kinetic energies. If only one object is moving, you only have one kinetic energy. If they fuse together, that's one object now. Is that clear? If they fuse together, we can consider that as one object. So those are elastic and inelastic laws. Yeah, Catherine, go ahead.
If like object 2 has no initial velocity, then there'd only be one kinetic, like the equation.
So if this is gone, take a look. She said if this is 0, then when you do kinetic energy initial, you're only using mass 1. Correct. Correct. So don't memorize. Do you see what I'm saying here? I really want you to understand this. Don't memorize it. Understand what's going on. If it's moving, it's got to have kinetic energy. If it's moving in the beginning, you call that initial. If it's moving at the end, call that final. Whatever's moving in the beginning, if it's 5 objects, it doesn't matter. You'd add all those kinetic energies together, and that's KEI. And then if only 2 of the objects after the collision, out of all 5, are moving, those 2 objects get added together to be KEF. So it can be any scenario whatsoever. I want you to be able to just think about what's happening and not memorize, what do I put in for KEF and KEI? There's no memorization for this. It's always going to be 1/2 mv squared, but it's a question of how many objects are actually moving and how many times you have to do 1/2 mv squared. Okay, how many objects themselves. That's my spiel. Okay? Now, I want to ask you what questions you have from the problem set and what things you want to go on. So you're the first one you were going to ask. So why don't you start? What was the first question you had? Do you remember the number? Because I have the textbook here. You gave me the hard copy then?
Yeah.
Okay. Any other hard copies I should be taking? Put them up there.
Oh, 7, 4, and problem
So you have homework for 7-4,
Yeah.
and then the problem set separately?
set.
You take pictures.
Yeah, I'll take
Yeah. If you're going to give me a hard copy, take pictures for your own sake so you can study with it over the weekend. Problem set. Thank you. And I saw your 7-4 and 7-3 already. Yeah.
Did you ever get my email? Because I emailed it to you.
7-4, right? Or 7-3? Because you emailed me 7-4. That's right. So I don't know what's up with your drive. So if you guys want to hang out for like a minute after class,
I fixed
You
it.
fixed
I'll
it?
show you.
yeah, I think I know what it's going to be.
I didn't have it, but for some reason, It's the same like
Yeah, it's a drive?
Yeah, some reason it got.
Yeah. Go to your drive folder and look for my folder, the one that we share, and click it and see if you can hit add to drive. If you can, that's probably the issue, but then you have to unsync your Notability account from drive and then resync it so that it then finds it as an option.
Well, I don't have my Notability account synced. I have it synced to like Dropbox.
Oh. So you're taking the route where you go to Dropbox and then you go to drive? So just add my folder to your drive, right click it or hit the dots and add to drive, and then it'll be an option for Notability instead. It makes it easier. Yeah, I know what you're doing. Thank you. Awesome. So come on, so start, go ahead.
Number 88.
Number 88 in chapter 7 we're looking at. Hey, by the way, no, it's fine, I got it. I thought I'd point this out. I didn't notice it until literally like 2 days ago. At the end of the textbook, I hope it's in yours, not just the teacher edition. Yeah, it's here. At the end of the textbook, on page, write this down, on page R39, there's a reference section at the back of your textbook. There's a lot of sample math problems. Remember how I was giving you math problems the last couple tests? You guys were like, can you give me some sample ones for the forces? We did it. And then for the energy stuff. There's a ton of math problems back here in what's called section R. And specifically for chapter 7, this is page R39. So there's a lot of great example math problems for chapter 7. I'd recommend those are good ones to look at over the weekend. Okay? R39.
Can you answer that?
Let me go first and then I will. Yep. So this is number 88, you said?
What's your help for this part? Are you gonna put like last time what you were talking about that? Like are you gonna put the song one so like
I'm going to put the...
like the solutions?
I don't have them, but if you want them and you're having trouble, let me know. Because the textbook publishes solutions. I can just email you what they say in the book.
Okay.
So if you work on a problem out of R39 and you want to ask me, just send me the question number, and it should be in my file set somewhere. That's where the problem sets come from. I used to write them by hand. The old textbook didn't have like electronic versions. So if it has electronic, I'll just send it back to you quickly like that. Yeah.
Thank you.
But I don't plan on writing them all by hand, is what I'm saying. So page 261, number 88, it says, a system has two objects. If the total momentum of the system is conserved, does this mean that the momentum of each object must remain the same? Explain. All right. Thoughts? Anybody want to help with this one first, and then I can take a stab and help you if you need? Again, the total system must be conserved. It says a certain amount of momentum in the system to start, so something must be moving. And the question is it possible for them to have the same, or should they have, or must they have the same momentum after collision? What do you think?
In like elastic collision, if like one of them was stationary initially and then it collides and then all the energy is transferred into the other.
So that.
Yeah.
So in this example, it shows us that this one had momentum to start, didn't it? So the total momentum in the system is whatever velocity this one has times mass to start. This one's not moving. And then after collision, that one started moving, right? So now there's no momentum here, and this one has the momentum. So the total system has a constant momentum, but it can be changed from object to object. So they don't have to have the same momentum for each object. This one had it and lost it. This one didn't have anything and gained it. The loss of one's momentum is the gain of the other's. Remember electrons from last year? When you said an ion was positively charged, what did it mean? It meant you lost an electron, right? You can't gain protons. Remember that whole idea? You can only gain or lose electrons. Those are the valence shells. So a proton or a positively charged ion simply lost electrons. Where did they go? They went to the other thing that gained the electron, right? That's like the concept here of conservation of mass. You were talking about conservation of charge with chemistry, just like conservation of energy last section. Yeah? So one object's loss equals the other's gain. We could have a 3-system object or 3-object system like this. Look, keep that in mind for the test. That's another possibility, right? Of 3 objects. The momentum in object 1 goes to 2, and then 2 goes to 3. So you can have several changes in momentum in a system. We haven't done anything mathematically, so that would be more like understanding, right? For a 3-system or 3-body system. Noel, last.
Yeah, when you're doing like the KEF,
Mm-hmm. Is this inelastic or elastic? The first table or the second table? Okay, so elastic. Go ahead.
the formula would be half M1 plus
Well, in elastic collisions, they don't combine, right? Aren't they separate after the collision? So after the collision, if they're separate, we have 2 separate objects after the collision. So this is what it would look like after the collision for an elastic setup, okay? Before the collision, if they're both moving, you have the same exact formula, but this is an I and this is an I right here. So just think about what's actually moving. If 2 things are moving, you've got 2 parts. If they fuse, then it's really only 1 object moving. So for inelastic collisions, the KE final is the 2 objects combined as a mass times their velocity squared. Only 1 object we think of it as because they fuse together and they're now moving together as one. Where are my Dragon Ball Z fans again? Anybody? Yeah, maybe some. Fusion, Goku, Vegeta, fusion. 2 objects coming together, takes energy. Takes energy, energy loss. It all goes back to Dragon Ball Z. That's the easiest way. You should just make a physics course all around Dragon Ball Z, right? I think that'd be a good class. There are weird college courses like that where it's like there's a whole course on psychology of a movie, literally. Like there was a course at Nova that was called the study of sociology and psychology of the movie Crash. Have you seen Crash? Anybody ever seen Crash? Phenomenal movie. I'd recommend it highly. It talks about like racism and things that exist in society naturally, especially things like law enforcement and stuff, and like how it's portrayed wrongly and sometimes not portrayed correct. I did not take the class, no. Engineers can't take those classes. We don't have room for it. Yeah. It was like an arts and science class or a humanities class, to be honest. Yeah.
For an inelastic situation, like let's say your final happens to be 5 and then your initial happens to be 5 and then you get like 0, is that cost?
Yeah. So inelastic will always show energy loss.
Okay.
Okay? Elastic, though, they should be the same.
Okay.
Yep. But inelastic, you're always going to have some energy loss. Because for 2 objects to join together, you have to have energy loss. Okay? Even if really they come together and they like stick together with Velcro, the little collision that occurs there is going to have energy loss. So let's make this point. Any real collision has energy loss. So nothing is actually elastic perfectly. But on the test, you're going to see that I'm going to say, in a perfectly elastic collision, or I can just say just an elastic collision, in an elastic, not inelastic. In an elastic collision. Okay, but in reality, everything has some energy loss. What else? That was a good question about the lab. Yeah, Alex.
Number 77.
77 says, we got a couple parts here, or is it multiple choice or something? It says, a net force of 200 newtons acts on a 100 kilogram boulder, and a force of the same magnitude acts on a 100 gram pebble. So same force, one on a really big boulder, one on a much smaller pebble. Part A says, is the change in the boulder's momentum in 1 second going to be greater than, equal to, or less than the change in the pebble's momentum in that same second? So we know that the change in any object's momentum is equal to the impulse. Yes? We're trying to figure out if the change in momentum is the same in both cases. Well, it looks like the force acting on the boulder is 200 newtons. The time period is in 1 second is 1 second. So the change in momentum is simply 200 kilogram meters per second on the boulder. If I do this for the pebble, mass is not changing. Mass is embedded in here somewhere. We're not looking for mass. This problem says, is the momentum change the same for both? This is the momentum change for the boulder. The pebble has the same force and the same time. So it's going to be the exact same momentum change. They both change with the same momentum. Part B, though, says, oh, choose the best explanation. I don't like that. I'm going to make a part B. Part B that I think about says, which gains more velocity, the boulder or the pebble? They both gain the same amount of momentum, which is 200 kilogram meter per second. This is the same momentum gain for both the boulder and the pebble because it's the same force at the same time. But which of them is going to get faster? Which of those is going to have? Yeah, because?
The mass is smaller.
Yeah, the mass is much, much, much lower. So if I went further to see this, take a look. Here's my situation. If I keep going, in both cases, the pebble and the boulder, what was the initial velocity? In both cases in this problem, the pebble and the boulder, what were their initial velocities? 0. So this is